Great, thank you, Justin. So our next speaker is quite exciting because we have Robin Rombach, who is coming to talk to us about Stable Diffusion and friends. So Robin is a research scientist at Stability AI, and although he has a background in physics, I think he got his PhD in computer science at the computer vision group in Heidelberg, which is where a lot of the work on things like VQGAN, Taming Transformers, Latent Diffusion Models, which then became Stable Diffusion, a lot of that work went down. So very excited to have one of the OG authors here with us. Robin, thank you so much for joining us.
Yeah, thanks for the intro. Actually, I don't have the PhD yet, so I'm still affiliated with the Compass group. But yeah. Okay, so I want to talk about a bit, of course, about Stable Diffusion, but more about like the underlying methods we developed in the research group. And also, as you already mentioned, VQGAN is closely related, so I'll also bring that up. And in general, I'm talking about this family of two-stage generative models, which Stable Diffusion is one instance of. So in general, Stable Diffusion is a text-to-image neural network. So this means that this model can be used to generate and also to modify images based on text inputs. And for me, it has been like really surreal to see this, what people call Cambrian explosion of creative AI with thousands of, different fine-tuned dream booth versions of the model, of repositories that tinker with the model and so on. It has been really cool, really surreal. And maybe one highlight that I just saw a few days back was this object tape to the wall diffusion model, which I think is kind of peak creativity. But yeah, let's look back on how we actually got there. And yeah, as I said, Stable Diffusion is a two-stage generative model, and I think one view to view this two-stage generative models is that they actually can combine domain knowledge and a general purpose generative modeling paradigm. So what this means is that the modeling is separated into two different stages, which are usually not trained jointly together, but you first train the first stage and then the second stage. So what this gives you is that you can actually in the first stage design something that is domain specific or data specific. So it can take in images or maybe video, 3D structures, whatever you're interested in, and map this to a so-called latent representation on which you then train a general generative model in the second stage, which can be a diffusion model, but also a transformer or other things. And this means that you can kind of separate the generative process from the process that requires domain knowledge. And maybe it's a nice way to actually collaborate with different backgrounds and so on. So one instance of this is this Leon model, which is a latent diffusion model for 3D shape generation. I think this was published yesterday or 2 days ago. It's latent space diffusion models of cryo-EM structures for structural biology modeling. And actually, another instance of that is Dolly 2. And this is like what Stable Diffusion is also about, is actually using domain knowledge of the image domain to compress images into a lower dimensional space in which it is very easy to actually do generative modeling. So Dolly 2 uses CLIP, which is a contrastively trained model to compress input images into this low dimensional vector space. And then they train a diffusion prior on this vector space to kind of invert this process. So why is it actually important to incorporate this domain knowledge when you want to model images? And let me maybe try to explain this with this example here, this image of the squirrel. But when we're interested in doing generative modeling of such images, it is important to capture the global structure of the image, but we're usually not that interested in modeling all the exact high-frequency local structures, so the texture here. So for example, in the case of the fur of the squirrel, the main thing that we're interested in is that it looks like realistic fur, but we are not really interested in the precise locations or interactions of these individual hairs. And using this insight can actually really help to train better generative models, because if we can get rid of these imperceptible high-frequency details in the first stage, then the generative model doesn't necessarily need to learn the distribution over them. And because these are kind of imperceptible details, it does not have to waste capacity on something that we do not see in the end anyways. This is kind of the general motivation behind that. And like our first work on that was VQGAN in the paper Taming Transformers for high-resolution image synthesis that we published 2 years ago. And I would like to briefly talk about this because the underlying motivation architecture is actually very similar to Stable Diffusion. So to avoid modeling these fine high-frequency details that would kind of lead to wasting model capacity, we introduced this VQGAN model, and VQGAN builds on another previous work which represents an image as a sequence of entries from a learned codebook. More precisely, we used the VQVAE architecture, which was introduced as a model for neural discrete representation learning. And in a nutshell, this approach relies on the straight-through gradient estimator and vector quantization to simultaneously learn this codebook and the encoder and decoder modules, which are convolutional neural networks. And after training this first stage model, this VQVAE, this will produce a compact discrete representation of an image from which you can take the image and code it into that discrete representation and decode back into image space from it. But VQVAE, as it was introduced, relied only on pixel-wise losses such as L2 or L1 losses. And using only that is not kind of using enough domain knowledge about images, because if we do that and reduce the capacity of the codebook too much, then we will have this typical blurry reconstructions. And if you want to do high-res image synthesis, we of course want to get we don't want to be bottlenecked by having blurry reconstructions. And to kind of overcome this issue, we actually need to avoid an objective which favors perfect pixel-wise reconstruction and would lead to averaging and blurring. And even more crucially, if you want to put the limits of compression and learning a nice discrete representation, we want to learn something that only captures the more global structure and gets rid of this high frequency details I already talked about. And to ensure that, we introduced like 2 additional losses to the original VQVAE architecture. One is the LPIPS loss, which is a perceptual loss. So LPIPS is a perceptual loss which has been demonstrated to align well with human perception. And then the other thing that we introduced is a adversarial training on top of that. So we introduced another discriminator, which actually is trained in a patch-wise fashion. So it's these local patches of the reconstructions of this VQGAN. And this ensures that we actually enforce local realism and don't have blurry reconstructions. And this means then that the total loss of this model is actually a combination of the VQ loss that is used to train the codebook, the reconstruction loss, and the adversarial loss. And because initially we found it extremely difficult to actually correctly weigh these terms, so we introduced a more dynamic strategy to weigh in the adversarial loss by calculating in the adaptive weight that we then apply to this adversarial term. And this adaptive weight is simply the gradient of the reconstruction loss with respect to the last layer of the decoder divided by the gradient of the adversarial loss with respect to the last layer of the decoder. And this means that the contribution of the adversarial loss is decreased as soon as the gradient of the GAN loss is larger than the one of the reconstruction loss. And another important part of it is that we actually warm up the training first by training only with reconstruction and VQ laws, and then as soon as the model has already converged to something that looks like good reconstruction but is not necessarily like realistic, we then add the adversarial objective to it, because this is kind of we found that this is the most stable way to do to train this model. And yeah, as an illustration of what this actually gives us, we can look at reconstructions of this squirrel that I was talking about as a motivation. So if we look at this paw of the squirrel here, we see that for a standard discrete VAE, which is not using perceptual loss or adversarial training, we see that the overall structure is actually good, but the local details are blurred out and the texture of the stone is not crisp. So this does not look like a realistic image, I would say, like a realistic natural image. And when we instead train this VQGAN paradigm that I introduced, we with like the same latent capacity, we achieve a very good reconstruction and realistic looking texture. And what this additionally gives us is that we can increase the compression level even further, and we still have a realistic looking fur, although the pose and shape is not perfectly aligned with the input anymore. Okay, so this is basically the first stage training, and in this work, like in Taming Transformers, we were training transformer models as the generative model in the second stage. And to do this, doing this is then actually really straightforward. So once we have the VQGAN trained, you encode your training images through the encoder, which gives you this discrete grid of codebook entries. You unroll them into a 1D sequence, and then you can train an autoregressive transformer on the sequences kind of top left to bottom right. And it's also easy to make this model a conditional model, like a text-to-image model. And one way to do that is to just prepend the conditioning tokens, so text embeddings, for example, to the sequence, or you could also use an encoder-decoder structure to do that. And then use the transformer to model the distribution over the discrete entries, and then decode with the pre-trained decoder back into image space. So yeah, we use that mainly to generate these high-res images of landscapes, because we were kind of compute bottlenecked while being at the research lab. But it's actually pretty cool that Google took this approach and used a slightly modified version of VQGAN, which is based on VisionTransformers, and trained a large-scale text-to-image model. And they showed that this actually is scalable and can produce really good-looking results. And I think the latest version of that is actually combined with the Imagine upscaler to produce really impressive high-res images. Okay, and so this was kind of the first work in that direction. The second was then high-resolution image synthesis with latent diffusion models, and it shares the motivation with VQGAN basically. So what it's kind of you can kind of view this as exchanging the transformer backbone with a diffusion model. And this gives you certain advantages, which I will talk about in a bit. But one more thing is that you can train this on a VQ embedding, so on a discrete embedding. But the more natural way maybe to do that, and which also gives you slightly better reconstructions in the first stage, is to use a autoencoding architecture which does not have a discrete bottleneck, so not a vector quantization layer, but which is regularized with a KL loss. So this is also what we use then for training Stable Diffusion. And we just use a very slight regularization to still have good looking reconstructions with good texture, but it ensures that the latent space is not arbitrarily scaled. But like adding the adversarial loss with this dynamic weighting and so on, this is exactly the same as in VQGAN. But there's one more thing that we needed to do to, because we were interested in text-to-image generation, to actually make diffusion models work for text-to-image generation. There was no architecture at this point which did that. So we came up with this modified architecture. We took OpenAI's ADM model, which was trained for class conditional synthesis on ImageNet. And this model came with self-attention layers in the UNet backbone. And we kind of replaced these self-attention layers with one-layer transformer blocks, which themselves consist of self-attention, cross-attention, and feed-forward layers. And these cross-attention layers helped or can be used to condition on arbitrary inputs, kind of. So one of them is like the natural way to condition on text is, I would say, cross-attention. So you can use this to condition on the outputs of some other text encoding model, which you can either train jointly with the unit, or you can also use a pre-trained one, like the clip text encoder that was used in Stable Diffusion, or some D5 encoder, or anything else. Yeah, and these are some text-to-image outputs that were actually then generated with Stable Diffusion. So Stable Diffusion is an instance of a latent diffusion model. It uses this architecture that I just introduced. Stable Diffusion uses a fixed clip text encoder to do that. And yeah, I didn't generate these samples. I collected them from a Discord server because there are people who can do this way better than me. But yeah, it has been really impressive to see what people can actually do with this model. And maybe one important kind of ingredient that I didn't mention yet is that these models only work when they are combined, work well, only when they're combined with something that's called Classifier free diffusion guidance. And this is kind of a cheat code that was introduced by Jonathan Ho and Tim Salmons. And intuitive explanation of what it does is during the denoising process, it pushes the model away from an unspecified or an unconditional model towards the conditioning signal, so towards the text that you give it. And this means that this process actually needs this unconditional model, which might seem like a disadvantage at a first glance, but actually it's really easy to implement this by dropping out the conditional signal at a certain rate. So for Stable Diffusion, we drop this 10% of the time during training. And this also comes only with a small additional cost at inference, because these scores, these model outputs can be computed in parallel, or if you're memory restricted, you can also compute them sequentially, but then it's a little slower. And yeah, here we see some outputs for s equals to 1, according to this classifier free guidance formula. 1 means that this is actually the standard diffusion case without this guidance, and we see okay, this doesn't look like a good looking generation. The prompt here was a panda eating fries in a restaurant. But if we turn up the value of this guidance scale, we actually arrive at something that looks like a panda eating fries in a restaurant, right? So this is super important to actually have this in the model. But yeah, Stable Diffusion is not restricted to, it cannot only do pure text to image synthesis, but it could also do in-painting. And the nice thing about this is you can, and I think Justin already talked about this, is you can actually take the pre-trained model and fine-tune it for these different tasks. So in-painting is one instance of this. You can then, because it's text conditional, the nice feature is that you can actually control what you want to have generated in the masked area. Another is semantic synthesis. We recently published a model that is conditioned on molecular depth estimates. So this gives you something that is a model that is really shape preserving. So you can give it an input image, infer this depth estimate with, it's actually using another neural network, and then condition the model on that. And yeah, as you can see, the shapes are really preserved for this one. And another version is upscaling, which is also very easy to implement, but just giving it a low resolution image. And there's one more nice application, which was not possible before when doing the transformer-based approach, which is image to image, or image-to-image translation. And this is based on something that was introduced in a paper called SBEdit. And it's a very simple recipe. So given some initial image, you would add noise to this initial image according to the diffusion schedule that you use to train the model. And this destroys some information from your initial image, but then you can actually reword this process with the pre-trained model, and using different text prompts, you can try to steer what the output looks like. So the cool thing about this is that it doesn't need like additional training, but can just be applied with a pre-trained diffusion model. And yeah, I did this initially with this sketch here of this landscape that I came up with. And it's actually really cool that you can control the style of the generation by simply changing the text prompt. So we can do a watercolor painting of a fantasy landscape. We can do a digital artwork by just changing to trending on ArtStation, or specify certain artists and so on. And yeah, this was, I have to admit, unexpectedly popular, but I think it's really cool to see that this can be used in such creative ways. So, for example, it was used to upgrade your child's artwork. There were a lot of interesting Twitter threads on that. And also, yeah, I just found it interesting how many creative applications people came up with. This is not actually not based on image, but just text to image. But just this text to color palette application where you could just enter an emotion or some abstract concept and get a color palette out of that is, I think, a very nice application actually of text to image models. People combined this with other techniques, for example, for video stylization. Then there was this, there are like even more websites right now like this, but the one that popped up pretty quickly was Lexi Carlile, which is kind of a library for samples generated with Stable Diffusion, and you can browse it and check the hyperparameters that were used to generate the samples, and try to use this as an inspiration maybe. It was really interesting to see this, how many plugins and UIs popped up, and ports to TensorFlow carriers ran on a Mac pretty quickly. It was used for lossy image compression, and also super interesting actually to see this being increasingly used as a benchmark for different inference engines and so on. Yeah, and what's next with this? I don't know how long like this specific Stable Diffusion architecture will be around, but I guess one very interesting direction that I'm excited about is actually making this faster during inference, because this has lots of practical applications, I think, for mostly all of the different creative applications that we've seen. And one way to do that is by distilling the model into a few-step denoiser model. And yeah, I'm actually happy to announce that we are working on that there's a collaboration going on with Chen Lin, who had a nice paper on distillation of guided diffusion models, and we applied that to Stable Diffusion, and there's good performance already with 4 steps only. And this model also folds this classifier-free guidance step into the model by simply, or by additionally distilling the classifier-free guidance step into a single step that is conditioned on the guidance scale. So this also decreases the costs actually of doing that. Yeah, and I think this is an interesting direction. Maybe it can be pushed even further. So yeah, that was my overview. Credits go out to like all the amazing collaborators, Patrick, Andreas, Dominic, Björn from the research lab. Of course, Hugging Face for the support, and so on, and all these open source libraries. So thanks for having me.
Thank you so much, Robin. Really nice talk. I think Jono has some questions to share.
Yeah, well, first off, you heard it here, folks. Distilled Stable Diffusion coming soon. Robin, thanks for sharing that. Yeah, I guess I had a question on sort of where you're thinking of looking next. I know you came from this transformer-based approach first to the latent diffusion models. Are you thinking that diffusion is going to be the way forward, or has Party sparked some thinking that maybe the transformer approach might be interesting? Is there a hybrid like Paella where you could do like a diffusion-inspired like multi-step inference with transformers? What are your sort of research interests going beyond like just the fine-tuning stable diffusion?
Yeah, absolutely. Yeah, good question. So yeah, I think there are two directions. So one of them is actually distillation, making this fast is super interesting, and then it's becoming really hard on the few step regime, and improving that, making it a real-time application, I think would be super nice. Like retaining the generalization abilities of the original model, but having it in real time would be nice. So this is like one direction. The other is we see all these different fine-tuned dream booth models. I think there are over 5,000 on Hugging Face already, 5,000 checkpoints, which is insane. And maybe there's a way of actually getting kind of this performance without needing to fine-tune. So I think this is also a super interesting direction.
Right, so something like what Justin is doing, where you're adding additional capabilities of not just depth conditioning, but maybe conditioning on images, conditioning on faces.
Yeah, all right. Exactly.
Awesome.
We've actually got a question from the audience, if that's okay, we could share it quickly.
Oh yes, we've got a minute or two. Yeah, perfect.
So the question is from Paul, who's asking, is there like a direction to sort of add numeracy? So can you, for example, have something like a painting with 9 apples? And I think in general, this idea of like compositionality and numeracy is kind of like as far as I know, kind of an open problem. Do you have some sort of thoughts there about, how we might integrate that information?
Yeah, I think one of the directions is to use increasingly powerful text encoders. I think the Imagine paper already showed that this is possible. The other is maybe you could combine this with like this conditioning techniques. You could condition on, let's say, the output of an object detector or something like that, which actually detects the objects and is able to count them. And then you could modify this by like just specifying the number of things that you want to have. So maybe these are like 2 different ways of doing that.
Awesome. So I think it's time for your compatriot, Patrick, to join the party. So thank you so much again, Robin. It's a real pleasure to hear from the creator of Stable Diffusion.
Sure. Thanks for the invite.
And yeah, see you next time.
See you. Bye.